Hi Venu, good evening, bro. So hello guys, hi, good evening, YouTubers, hi. So yep, just a moment. Yes, done. So hello guys, hi everyone, good evening. So hi Kavana, hi everyone. So hi everyone, good evening, good evening. So hi YouTubers, hello, good evening. Hi Bhargav, hi Priyanka, hi Lakshmi. So we'll be going live by 5 p.m. exactly. So till then, please try to go join. I mean, yeah. So waiting for all Zoom audience to join. So once they join, we'll start the class live. Okay. So we have some set of questions here displayed. I want every one of you to take the test of these questions. So I hope everyone have come prepared to the class, right? Hi, good evening, Prajwal. So Prajwal, ಹೇಗಿದ್ದೀರಾ? Okay, cool. So hi guys, hi, good evening. So everyone, please try to connect to the audio and let's begin the class exactly by 5 p.m. Right, so it's 5 p.m. and waiting for all the Zoom audience to connect. Please, ask your classmates to join the class soon. Hi Prajwal, good evening. So ask your classmates to join the class soon so that we can start the class. Hi YouTubers, good evening. So everyone, I hope everyone is doing great. So how's your preparation going on for both, for all, for your studies as well as for the festival? I hope everyone is starting to prepare. I mean, started preparing for Deepavali, right? Yeah, I won't call it as Diwali. I will call it as Deepavali. Cool guys. So yeah, I hope everyone have tried to study for Gauss. I hope everyone have revised Gauss Law once in your home. Come prepared with a pre-reading. So I'll be giving you, as displayed here, there are some set of 4 questions for you guys to check whether you have studied or come prepared to the class or not. Before that, I want everyone to give the technical check. I have launched the technical check, guys. Please check. Let me know if my voice is clear and audible, and if the blackboard is visible. So there's no blackboard, just is the computer screen which is visible. Yes. Good evening, Bhargav, Priyanka, Lakshmi, YouTubers. Hi. So yes. So guys, yeah, in our previous class we had studied about something about the electric flux, right? So we had studied something about the electric flux. So again, we'll be again recalling all the concepts which we had studied about electric flux, then also about the electric field. In today's class, we'll be learning about applying Gauss law. So we'll be starting with Gauss's law. What is Gauss's law? Where can we apply Gauss's law? We'll see the derivation for Gauss's law in some 2 conditions. Say we'll be solving only for charge sphere today, and we'll be keeping the electric field due to infinitely charged wire and the plane surface for the next class. So till then, yeah, we'll solve all the derivation. We'll give all the derivations today, and again we'll solve few problems which are based on what we learned today. Okay. Okay, guys, I'm going to end the poll of the technical check. So, and again, yep, I'm going to launch the poll for recall test. Or yeah, so this is known to Zoom audience, and I want everyone, the YouTube people and also the Zoom people, to answer your questions. So if there is no options available, please answer in the chat box. If there is no, okay, do one thing, answer all questions in the chat box. Since there is no question options available for these, please mark your question number and answer. Okay, so 4 minutes for 4 questions. Your time starts now. Everyone, YouTubers and Zoom audience, please try to answer. So according to Gauss's law, phi e is equals to integral of closed integral of e dot ds in n cap direction. Here the normal vector is usually taken dash the direction of the closed surface. Yes, correct, Amit, correct. Yeah, only Amit had answered. Others guys, try to answer. Others guys, please try to answer. So YouTube people, please try to answer all 4 questions. Give your answers as question number 1 answer, question number 2 answer, question number 3 answer, and question number 4 answer. Please mention the question numbers of which you are going to answer. Everyone. Yes, Arun, correct. Guys, come on, answer. See, there are yes, there are many YouTube. I mean, there are many students here, and yet no one is answering so far. Okay, so we'll start solving the answers. Okay, we'll try to check the answers. So yes, please tell me what's the first question. What's the answer for first question? Answer for first question, guys. YouTubers, please try to answers. Zoom people, only two people have answered. Only Arun and Amit have answered. Others try to answer. Okay, according to Gauss's law, the normal vector is always taken. Yes, it's always taken outwards. Okay, so it's always considered as outwards direction. Okay, we'll study about this today. Next, according to the Gauss's law, the net electric flux through a closed surface is given by Q by epsilon naught. Here, Q denotes the which type of charge? In Gauss law, what does this Q signify? So what does this Q signify in Gauss law? Bhargav, come on, Priyanka, Bhargav, Lakshmi, try to answer. Here guys, Prajwal, Manju, Rohit, Arun, try to answer. Teju, sorry, Tejas, Preetu, everyone please try to answer. What is the answer for second question? According to Gauss's law, yes, correct, Arun. Others, please try to answer, guys. You are not answering. If you want, I can launch a poll for that. So for second question, guys, try to answer. Prajwal, no, check your answer. So this part is not yet completed to you guys. So this is a spot test. In spot test, we take the test of class. I mean, we take the test of questions. I mean, we give the questions in such a way that these are the topics which we are going to study today in our class. Okay. So these spot tests would be based on the questions which we are going to study today, or the concepts which we are going to study today. Okay, and the second answer is, I got only one correct answer so far, guys. Others, please try to answer. Prajwal, Manju, Lohit, Amrit, Amit, Priyanka, Tejas. Hello, Tejas, answer, Mada. Guys, try to answer. Okay, second question answer is yes. The second question answer is B, option B. Okay, the charge enclosed. So only one student had given me the right answer. The charge enclosed inside the closed surface. So we'll be studying about this. Then Gaussian's law is valid for all charge distributions. Okay, correct, Manju. Yes, so Manju, Amit, and others had given this answer. Gauss law is valid for all charge distributions. Okay, next, magnitude. Magnitude of electric field at any point near a charged infinite sheet with a surface charge density of sigma depends on the distance of the point from the sheet. True or false? Magnitude of electric field at any point near the charged sheet with a surface charge density of sigma depends on the distance of the point from the sheet. Is it true or false? Yes, it's true. As my distance increases, see, electric field in general, electric field varies inversely proportional to r square, right? As my distance increases, what should happen? My electric field should decrease, guys. Okay. Yeah, these were the answers. Only Amit and Manju had given me the answer. Amit, Manju, and Arun had given me the answer. YouTubers, please try to be active. So this is about today's class anyway. So we'll start with electric flux again, guys. So in our previous class, we had started with electric flux. What was electric flux, guys? Tell me, what was electric flux? So we gave an example of water faucet. Say, if I have a water pipe, if I have a pipe and my water flows through this pipe with some velocity v. If my water flows through the pipe with velocity v, then the rate of flow of liquid or rate of flow of water is given by AV cos theta, where A is the area of cross section, V is the velocity of the liquid, and theta is the angle made between the velocity vector and the normal vector. So yesterday we also checked what is the normal vector. So if we have an area A, then where should we take this area vector as? What is the direction of area vector, guys? What is the direction of area vector we consider? Please respond, guys. So we consider the area vector to be normal to the surface area. Direction is always normal, okay? Normal to surface area, okay? Then next we studied about the electric field lines or electric flux. What is electric flux, guys? What is electric flux? Please reply, everyone. Please reply. What is electric flux? Electric flux andre ಏನು? Guys, what is electric flux? Phi. So electric flux is given by the Greek alphabet phi, okay now? So electric flux through a surface is nothing but, say, the number of electric field lines passing through a given surface. Say I have a surface A. So I have two surfaces, surface 1 and surface 2. So the surface area of 1, I have first surface is alarm. So its surface area is given by A1, okay? Let A1 be the area of surface 1, okay? Similarly, let A2 be the area of surface 2. Then the number of electric field lines passing through this surfaces, say this electric field line is entering this surface, leaving this surface, entering this surface here, leaving this surface here. Similarly here, one electric field line is passing through this A1 and leaving this A1. Then the total flux, the flux through this surface is given by flux is directly proportional to number of electric field lines. So number of electric field lines. So guys, what is the flux in surface A? What is my phi 1? What is the electric field lines? How many number of electric field lines is in surface A? Or flux in A is given by phi equals to, or phi is directly proportional to how much? How many electric field? So if n is the number of, if I can write phi is equals to, phi is proportional to n times of E. So what is the value of n here? What is the value of n here, guys? Please try to be active, guys. YouTubers, yes, correct, Arun. So it's 1 times of E, right? So there is only one electric field line is passing through this area. So have my phi1 is proportional to 1E. Similarly, in the case of second area, we have phi is proportional to 2 times of E. Why? The number of electric field lines passing through this is 2. Okay. Next, we had learned about the factors affecting the electric flux. So all these points we had learned in the previous class only, just I'm revising. See, the electric flux passing through the surface depends on the area of the surface, right? If my area increases, the number of electric field lines passing through this area also increases, right? If my surface area increases, the number of electric field lines passing through this surface also increases. Then the flux is given by phi is equals to E dot A, or yeah, flux is nothing but the number of electric field lines passing through the given area. Okay. Next, guys, if lesser surface area, if the surface area is very less, if the surface area is less, then the electric field lines passing through this area is also less, then my electric flux is also less. Okay. Then the second factor which is affecting is, yes, so electric flux depends on the angle made by the surface and the electric field lines. So the angle theta made between the electric field lines and the electric surface. See, somebody asked, sir, if my theta is given like this, right? So we know phi is equals to E dot A, that is EA cos theta. Alva. So now in this case, if my theta decreases, what happens? If my theta decreases, what happens? As my theta between E and A decreases, my flux cut through this is less, right? The electric field lines cut through this surface is less, then my flux will also reduces. But if my theta is 90 degree, then the flux passing through this, or the electric field lines passing through this surface is more, then the electric flux is also more, right? But yesterday somebody asked in chat box in YouTube, I guess. It was not asked in your normal class, so it was in YouTube. Sir, if theta is equal to 90 degree, then my cos theta value will be 0. Now, how will my flux be maximum? Guys, tell me, is my when my theta is 90 degree, the angle between the surface area, see, if this is my surface area, angle between the surface area and the electric field lines is 90 degree. Okay, so this is 90 degree. Now what will be the value of my flux phi? Is what will be the value of my flux? Will it be 0? 0 agata. Will my flux be equals to 0? ಏನಪ್ಪಾ Arun? Please guys, reply what's the answer. So will my flux be equals to 0 in this case? No. Why not? Why is my flux not equals to 0? So yesterday guys in YouTube somebody asked this doubt, sir, if theta is equals to 90 degree, then I'll get my flux 0 now. No, it's not 0. Why? Because we are not going to consider this angle between the surface area and electric field. Which angle are we going to consider? So we are going to consider the area vector angle, n cap, right? We are going to consider area vector angle. Yes. So, but which angle are we going to consider, Priyanka? We consider area vector angle, right? Area vectors angle. So what is my area vector angle? Say if my surface is like this, and what is my area vector, or what is the angle between my area vector and electric field in this case, guys? Tell me, what is the area vector angle in this case? So if this is my surface is horizontal, perpendicular to that of my electric field, then what is my area vector angle? Please reply. Someone, yeah. So my surface area angle will be parallel, right? My surface area angle n cap, if you can see here, my surface area angle n cap will be parallel to that of my electric field. Then what is my theta value here? This theta. I'm talking about this theta, not this angle between surface and electric field line. I'm talking about the surface area vector, angle between area vector and electric field line. Theta is angle between area vector and electric field line, right? So what is my theta here? In this case, angle between n cap and E is 0 degree, right? My angle between electric field and surface area vector is 0 degree. So my theta will be 0 degree here. Then my flux will be what? Maximum or minimum? Flux maximum irata, minimum irata. Yes, flux will be maximum in this case. Got it, guys? Any doubt here? Any doubts here? Any doubts so far? Okay. Next, the electric field strength also depends. Okay. The electric flux also depends on the electric field strength. If my electric field strength is more, what happens? If my electric field strength is more, there will be more number of electric field lines. The number of electric field lines increases. If my electric strength is more, the number of electric field lines will increase. And very large, since there are large number of electric field lines, in small surface also, my electric field lines is more, then my flux will be more, right? If my electric strength increases, number of electric field line increases, and hence flux also will be more. If electric field strength is less, yes, in a given area, then my flux will also be less. Okay, this is the condition. These are the three factors which affect the electric flux. Okay, next, guys, come on. So we want an expression for electric flux. So what is an expression for electric flux? So to get this expression, we consider this. So we'll consider a plane surface of area A. We'll consider a plane surface of area A. Let n cap be the direction of my area vector. So if I have my area vector A, in which direction will be my area vector, guys? In which direction will be my area vector? So my area vector will be always normal to the surface area, right, Prakash? So my area vector will be always normal to the surface area, and the electric field will be, say, if I consider my electric field is along this direction, then the angle between the electric field and the area vector will become my theta, and E is my electric field strength, and A is the surface area. Then the expression for electric flux is given by phi is equals to EA cos theta. Okay, phi is equals to EA cos theta. So what is the SI unit for this, guys? Then what can I write my SI unit as? My SI unit could be coulomb meter square. Okay, SI unit could be coulomb meter square. So this is the expression for my electric flux. Okay, got this, guys? Please click on yes if you have got this. Yes, cool. Next, we define the electric flux by using the area vector. So yeah, we have to define an area vector. So why should we need an area vector, guys? Why should I require an area vector first? Why should I require an area vector? say I know flux phi is equals to EA, E dot A. So if I have a vector and a scalar, can I apply dot product here? Can I apply dot product rule here if I don't have another vector? Yes, no, Anjali. Yes, if I have my flux equation as flux is equals to number of electric field lines passing through given area, then yeah, if I have one vector and a scalar, yes, can I multiply them directly? So I couldn't multiply them directly, and I can't predict my exact location of my electric flux direction. So I'll consider an area vector A, whose magnitude is nothing but the area of surface, and n cap, whose direction is always normal to the surface. Okay, whose direction is always normal to the surface. Cool. So this is my area vector A. Next, then the expression for electric flux is given by phi is equals to E dot A, that is EA cos theta. So we'll consider one more thing here in this expression. My electric field, we'll consider one thing. My electric field will be uniform in this condition. Okay. When I write phi is equals to E dot A or EA cos theta, so this condition, this formula is applicable for which condition? For which condition is this formula applied? Guys, reply. Zoom people, please reply. For which condition is this equation applied? So this condition is okay. This equation can be applied only when my electric field is uniform or constant. Okay. So what can I use for the cases where I have non-uniform electric field? Say if I have non-uniform electric field, how can I apply my electric flux equation? What should I do? Yes, correct, Priyanka. Correct, Ramakrishna. Ready. Cool. So what should I do if I don't have an uniform electric field? How can I apply my electric flux equation? Hello, guys, please reply. For non-uniform electric field, the flux also varies, right? So for non-uniform electric field, my flux varies. So for non-uniform electric field, we use the integration. Okay, we use the operator integration. So we'll consider how to apply in this case. So if I have very large surface or very huge uneven surface, say this is not a uniform surface, it's not a regular surface, I have some arbitrary shape. Now what happens? I have charge distributed throughout this surface. So what happens to the electric field, guys, in this case? Is my electric field same throughout the surface? Is my electric field same throughout the surface? Please reply. Is my electric field same throughout the surface? Or if I have a very huge surface, can I try to find the electric field at each and every point and try to add them? Yes, that is possible, but it is very time consuming. So what I do, I'll consider in both the cases. In both the cases, what I'll do, I'll consider a small surface area dA, assuming, say, suppose I'll consider this sphere example. So I have a solid sphere, or yeah, yes, correct, Karthik. So I have a solid sphere. Now I want to find the electric field or electric flux through this solid sphere. But this is very huge solid sphere. Huge solid sphere. Now, how can I find the flux? So to find the flux, see, in each case, my electric flux, say in each case, my electric field magnitude is varying, right? So what I'll do, I'll consider a small surface area, dA, and I'll assume that the electric field through this small surface area is constant. Okay, my electric field to this small surface area is constant. Then, I'll try to integrate this. I'll try to integrate with the function phi is equals to integral over the surface area with the electric field. I'll try to integrate the electric field, magnitude of electric field at this dA throughout the surface. So if I try to integrate throughout the surface, what would I get? I would get the electric flux over the entire surface. Okay. So this is how I try to find the electric flux. Yes. Correct, Priyanka. Correct, Lakshmi. Yes. This is how I try to find out the electric flux throughout the surface, throughout a very large, huge surface. So I use the integration. Okay. The SI unit for electric flux is given by volts meter or newtons per coulomb meter square. Okay. Please remember this. Okay, guys. Next. So, what is the electric flux through a closed surface? Say we are tending towards Gauss law. Say if I consider an electric flux. So what is an electric flux, guys? Electric flux is nothing but number of electric field lines passing through a surface, right? Suppose I consider a surface. So I consider a surface area A1. Okay. In this A1, how many electric field lines are passing? Guys, count and tell me. How many electric field lines are passing in this surface area? So if I try to name 1, 2, 3, 4, say there are 4 electric field lines passing, right? Now, how many of them contribute for the electric flux only along right side? So if I assume my electric flux is only along right side, how many of these electric field lines contribute to that? How many of them contribute to that? 1, 2, 3, right? So 3 of my electric field lines contribute to the flux towards right direction, right? Then what is the net flux? What is the net flux in the rightward direction? Tell me this, guys. Everyone, please try to tell me what is the net flux in the right direction, only along I cap direction. Yes, correct, Ramakrishna Reddy. Correct, Madhavi. Come on, guys, please answer. So how many of the, what is the net electric flux along the rightward direction, along the I cap direction? What is my net flux along I cap direction, guys? Tell me. So it should be the summation of the net electric field is the summation of all electric field lines in the given direction. Okay. Say here I have 3 electric field lines moving towards right. I have 3 electric field lines moving right and 1 electric field line moving left. So what is the net electric field, guys? 3 moving right, 1 moving left. What is the net electric field? E net will be, yes, 2, right? My flux would be having a magnitude of, then my 5 flux would be integral of A 2 times of I cap dot dA. So this way I'll find my net electric field. And what would be the direction, guys? What would be the direction? What would be the direction? So in which direction would I have many electric field lines? So yeah, in the direction where I get my maximum electric field lines, that would be the direction I have my electric flux. So in this case, this is I cap, but in general, I'll take it as positive n cap. So here it's in the positive n cap direction. Okay, yes, correct, Madhavi. It's towards right. So I'll consider it's always towards n positive n cap direction. Suppose I have one more electric flux. Okay, guys, tell me. Suppose I have one more electric field line in this direction. Now, what would be the direction of my electric flux? Suppose I have one more electric field line in this direction, from right to left. What would be my flux in this case? What would be the direction of my flux? Yes, correct, Likita. Correct, Pakesh. Correct, Karthik. It's still in the positive I cap direction only. Correct, Ramakrishna Reddy, Priyanka, and Madhavi. Cool. Awesome. So next, what happens? So electric flux through a closed surface. Now, if we have a closed surface. Suppose I consider I have a closed surface. Now what happens to the electric flux in a closed surface? How should I consider? So we apply Gauss's law here again. So we have not yet started with Gauss's law, but this stands as a basic for Gauss's law. What happens? Say if I want to find the electric flux to a closed surface, what I should do? So let us consider a solid sphere and let there be a dipole. So I have a dipole present inside a solid sphere. Now, guys, say I have a dipole inside a sphere. The electric flux inside the sphere can be given by which? Yes, correct, Karthik. We'll come to that. So the electric flux can be given by phi is equals to E dot dA. Then the direction of area vector. So guys, I have to make one point here. For closed surfaces, the direction of area vector will be always outwards. Okay, please make a note of this. The direction. So we had a question of on this. So we had a question on this. Yes, Priyanka, correct. If there are net, okay, if there are three, so I have a question, guys, from one of the students. Say if I in a surface, if I have three electric field lines going towards right and three towards left, what would be my net electric field? There are three electric field lines going right, three electric field lines going left. What would be my net electric field? What would be my net electric field? Yes, my net electric field will be zero. If my net electric field would tend to zero, my flux will also be zero. Hope I answered your question, Priyanka. Cool. Say, guys, everyone, please make a note of this. My electric flux is always pointing outwards in case of any closed surface. Please make a note of this. This is very, very, very important. The direction of area vector is always normal and outwards in the case of any closed surface. Okay, this is very, very, very important point. Okay. Yes, guys, cool. Yes, there will be no electric field at all, right? So sir, if there are equal number of electric field lines perpendicular to field line, okay, direction perpendicular to field line, yes. See, I have my electric field lines. I didn't get your question, Karthik. Karthik, ನಿಮ್ಮ question ಅರ್ಥ ಆಗಿಲ್ಲ ಏನು ಹೇಳಿ? So if there are equal number of electric field lines, then the electric field lines are perpendicular to, okay, the electric flux is perpendicular to field lines. Hanga, please let me know your question. I didn't get the question properly. So yeah, in this case, guys, yep. In this case, what's happening? My net electric field. So there was a continuation. So what happens in this case when I have a solid sphere and a dipole present? The electric flux inside the solid sphere. The electric flux inside the solid sphere is given by phi is equals to integral E dot dA. In this case, the net electric field, see, the number of electric field lines which are entering is equal to the number of electric field lines which are going out. Not necessarily, Karthik. No, not always. So my direction of the direction of area vector will always be pointing outwards. Okay. So direction of what are you asking, Karthik? Direction of which are you asking? If you could tell me. Okay, direction of area vector will always be outwards. Okay, guys, direction of area vector will always be outwards. Okay, it's always outwards. In which condition? So if I have a closed surface, my direction of area vector dA will always be outwards, pointing outwards. Okay, this is compulsory point. Okay, say yeah, in this case the net electric flux, sorry, the net electric field entering the closed surface and leaving the closed surface is same. So net electric field inside this sphere will be 0, then my flux will also be 0. Okay, guys, got this? Yes, correct. um Maybe, may not be, Karthik. So my direction of area vector may be or may not be perpendicular to field lines, say in any closed surface. Say if I consider some arbitrary shape, okay, some any arbitrary shape. So um, I'll consider an amoeba. So suppose if amoeba was a solid surface, then I had a point charge inside this amoeba. So what happens? My electric field lines would be in all directions, right? If this is a point charge of positive magnitude, my the direction of electric field would be in all directions. Now, if I consider a small area vector dA, this small area vector will be always pointing outwards. Now, tell me, is it in any way perpendicular to electric field lines? Iralapa. Karthik, simply it won't exist. So just remember this, my area vector will always be outwards, pointing outwards in any closed surface. Okay, good. So next I have a question for you guys. I have an answer also. Okay, a point charge. I don't know, I forgot to give. Okay, give me the reason. Okay, I forgot to put animations, I guess. So a point charge q is kept inside the center of a sphere with radius r. So I have a sphere. So I'll explain this question. Okay, a point charge is kept inside the center of a sphere. Say I have a sphere. Inside this I have a point charge q with radius small r. Say this sphere radius is small r. Now I have another bigger sphere of radius capital R. Okay. Now my point charge is still here inside a small radius sphere, and this small radius sphere is inside a bigger radius sphere. So R is greater than R. Then the electric flux through this sphere with radius small r is phi 1. So what are they telling? They are telling the electric flux because of this small charge q inside this small radius r, inside the sphere of small radius r is phi 1. Yes, yes, correct, Karthik. So again, since my electric field due to this small radius, I mean bigger radius r is phi 2, what is the relation? They have asked what's the relation. So yes, the relation is phi 2 will be equals to phi 1. Now tell me the reason why is this happening. So Karthik has correct answer. So tell me the reason, guys. Tell me why is this happening. Okay, I got one answer. YouTubers, please try to answer. Why is my phi 1 equals to phi 2 in this case? How many of you got this answer actually? How many of you guessed this answer? This is the actual answer. Anta ಎಷ್ಟು ಗೊತ್ತಾಗಿತ್ತು? Yes, correct. So, guys, what was the expression for phi we studied now? So, ಇಲ್ಲಿ ತುಂಬಾ ದೊಡ್ಡ explanation ಇದೆ. I'm not going to. Yes, there is a very big expression. So I am going to just it will be shared in your notes. I'll give you a quick explanation of what's happening. So what is my phi, guys? Flux is nothing but electric field times area, right? Electric field times area. This is my flux. Okay, I'm giving the explanation why this is equal. So if my flux phi is equals to E dot A, what is my electric field general expression for point charges? Say here it's given a point charge, right? Q. Yes, correct, Priyanka. Correct, Madhavi. So what is my electric field due to a point charge? E is equals to K times Q by R square, right? ಹೌದಾ? Correct, guys? So if I try to simplify, if I try to take the proportionality, my electric field is proportional to R square, inversely proportional to R square, right? Since my electric field is inversely proportional to R square, then what is my area, guys? You know, what happens with area? How my area varies with respect to distance. My electric field is inversely proportional to distance, and my area is directly proportional to distance. So if you take these two, in case of flux, what will happen? Flux will be proportional to 1 by r square times of r square, right? My r square cancels. My flux will be only, my flux only depends on the charge q here. My flux depends only on, it's proportional to only the magnitude of charge q. Okay. Guys, anyone requires any repetitions? If anyone did not follow, please let me know. Artha aita? Understood? So my flux depends only on the magnitude of charge. So if you have time, please go through this. Yes, charge is same. Oh, correct. So the charge is same for both the electric, both the surfaces of both the spheres of radius r and capital R. So yes, so that's the reason why we get the same flux. Okay, guys, cool. So next we have Gauss law. So I'll be starting with Gauss's law. So what is Gauss's law, guys? Why do we require Gauss's law? Let's have a discussion now. So why do we require Gauss's law? What is Gauss's law and why do we require Gauss's law? So there was G. Friedrich Gauss. Okay, yes. G. Friedrich Gauss, a French physicist, gave this expression. So this became his expressions or his observations became Gauss's law. So actually, when we study Ohm's law, when we study Gauss's law, when we study Newton's law, these laws were not given by them. Actually, they gave an observation. But today, in modern world, what happened? After long generations of say these all these innovations or inventions happened some decades ago, many decades ago. So it's nearly centuries ago, I can say that. So these not, yes, so they did not, they gave just their observation and they published their notes. So what happened with the time, this changed to law. Whenever someone wrote the textbook for us to study, they gave it as a law. But actually these guys did not give any law, they just gave an observation. Okay, now what is Gauss's law? So Gauss's law helps us so Gauss law is the law. So Gauss law gave an observation that flux, electric flux is proportional to electric field lines. Then how much is it proportional? The electric flux is proportional, will be equals to E times of area. How much area it passes through? How much area my electric field lines passes through? That much amount of flux I'll get. This observation was made by Gauss, and and this was improvised. So so the Gauss's law helps us in calculating the net flux. So Gauss's law helps us in calculation of net flux in where? Inside a closed surface. So if we had seen earlier in our earlier classes, we had seen that in our earlier classes we had seen that the number of the steps we had taken to find the electric field, the electric flux, electric potential, etc. was very high, right? It was very tedious and it was very time consuming. So Gauss's law, what it will do is it will eliminate that all unnecessary steps. It will give us the direct expression for electric flux in a closed surface. Okay, so let's start. So what happens inside? Okay, to derive the Gauss's law, let's consider a sphere. Okay, in this case, we'll consider a sphere. solid sphere or hollow sphere. Let's consider a hollow sphere. Okay, inside this hollow sphere I have a charge q. Let us consider a hollow sphere of radius capital R. So it has a radius of capital R. I'll use some dark background. Yes. Let R be the radius of this Gaussian surface. Then, or let's keep small r. Yeah, let small r be the radius of this Gaussian surface from the center. Now let there be a charge, a unit charge of magnitude plus q. So let there be a charge of unit magnitude. Say I have a charge of plus q. Now this charge emits electric field in all directions, right? This charge emits electric field in all directions. Now we have to consider, yeah, area vector for this. How to consider area vector? Guys, tell me how to consider area vector. We'll consider a small surface area dA. We'll consider a small surface area dA and let n cap be the direction. So n cap be the direction of what? Area vector. So my area vector is always acting outwards. Then such surface which is closed and which is having an charge enclosed inside it. So what did I say? A charge enclosed inside it. What do you mean by this? What do you mean by this statement, guys? So I have a charge. I keep the charge inside this closed surface. Okay, if I keep a charge inside a closed surface, then I can apply Gauss's law to find its flux. So what is flux? Flux is nothing but the number of electric field lines times the area. So guys, if you see what's happening here, so if I consider my area here, and if I have an electric field also in this direction, right? Since this is a positive charge, there will be electric field lines in all directions. Now, what is the angle between this electric field line and this area vector, guys? Tell me. What is the angle between the electric field line and the area vector? What is theta? See, my electric field lines is in all directions. Okay, it's even in this direction. It's in this direction. Since this is a point charge, my electric field lines are in all directions. Now, if I consider an area vector here, so what is the angle between this electric field line and this area vector? N cap. Guys, always remember my area vector is always perpendicular to that of my surface area. So area vector is always normal to surface area. Since it's normal to surface area, it's parallel with electric field line, right? My theta will be 0 degree since my n cap is parallel to electric field lines, right? So my n cap is 0 degree. Now my flux, we know that flux phi is equals to closed integral. So guys, how to represent closed integral? This integration with the bubble. Integration with the bubble sign shows it's a closed surface. We are integrating over a closed surface. So integrating over a closed surface. Integrating a closed surface is represented by this symbol. Now, if I try to integrate and try to find the flux, phi is equals to closed integral of E dot A, then my E. What is my electric field E, guys? What is the electric field E of a point charge? Electric field E for point charge is given by E is equals to K times Q by R square, right? Right. So this is the surface integral. Correct, Madhavi. So the electric field line, so I'll substitute the value of my electric field line. I'll get the flux through this. The flux passing through this closed surface area is given by phi is equals to integral q by 4 pi epsilon naught r square dA, where A is the area vector. Then, what is my area of sphere, guys? What is the area of my sphere? Surface area of sphere. Yes, it's given by 4 pi r square. Now, yes, correct, Rakesh. So what happens? My 4 pi, and 4 pi here also gets cancelled. Then what's remaining? And r square also cancels, right? So 4 pi r square and 4 pi r square in numerator and denominator cancels. I'll be remaining with the expression for Gauss's law, that is given by phi is equals to q by epsilon naught. This is very important, guys. This is the expression for Gauss's law. So this was the observation which was given by Gauss, yes, to find the electric flux. And this is true for, this value is true for all closed surfaces. This is true for all closed surfaces. Okay, guys, make a note of it, please. Everyone, yes, cool. So we can conclude that the flux is independent of the radius of the sphere. So what was the observation? So this is the observation from Gauss's law. This is the observation we get. We can conclude that the flux is independent of the radius of the sphere, and it only depends on the charge enclosed inside the sphere. So my electric flux phi is independent of radius, and it only depends on the charge enclosed inside the sphere. Again, guys, I'm telling the charge should be enclosed inside the sphere. So what is the given condition? My flux will be always Q enclosed by epsilon. This is the given condition, guys. Please always remember to write Q enclosed. Okay, whenever I consider my charge in considering a Gauss's law, the charge should be always enclosed inside a solid, inside a closed surface. Okay, the charge should be always closed inside, should be always present inside a closed surface. This is a very, very necessary condition to apply Gauss's law. Very, very important and necessary condition to apply Gauss's law. What is that? Another, the charge should be enclosed inside a closed surface. Okay. Now, to apply Gauss's law, say we'll try to apply Gauss's law. So here we said that the Gauss law can be applied to any closed surface, right? So we'll check how it is done. So the Gauss law states that the expression for the electric flux is given by phi is equals to q by epsilon naught. So this should be q enclosed by epsilon naught. Okay. Nice. So the Gauss law says that the expression for phi flux phi is equals to q enclosed by epsilon naught. So this is true for all closed surface. And how to apply Gauss's law? So let's again consider a closed region. Okay. Let us consider a closed region and let Q1 and Q2 be the two charges. Okay. Now, guys, what do you think the expression for what do you think the flux through this surface, or what is the amount of electric flux inside this closed surface would be? Apply Gauss's law for this and tell me the answer. Everyone, please try to answer this. So apply Gauss law to this and tell me the answer. Yes, Karthik, we'll study all the three cases. Okay, we'll study for application of Gauss's law through a solid sphere, then infinite long conductor, and electrical and also the plane condition. So we have all three in our syllabus. We'll study that. How Gauss law can be applied to the plane is also will also be studied. Okay. Okay, guys, come on, tell me what is the electric flux? Tejas, answer. Try to answer. What is my flux in this condition? Phi equals to. Everyone, yes, correct, Ramakrishna Reddy. Cool. Madhavi. Yes, correct, Madhavi. Madhavi, correct. Bhargav, correct. Ramakrishna Reddy, correct. Guys, in Zoom class, please answer. Students in Zoom class, please answer. Try to answer. Yes, guys. So the electric flux, if I try to see what's happening here in this condition, we have, yes, correct, Tejas. So we have how many charges enclosed inside the closed surface? How many charges do we have inside the closed surface? There are only two charges, only Q1 and Q2 are inside the closed surface, right? Only Q1 and Q2 is inside the closed surface. What happens to Q3 and Q4 then? So what happens to Q3, Q4? Why shouldn't I consider this? Why shouldn't I consider this? Yes, there are only two charges inside the closed surface. But why shouldn't I consider this? Yes, my Q2 and Q3 and Q4 are not enclosed. So for not enclosed condition, what happens? So will there be electric field in for Q2 and Q3 and Q4 also? Yes, will there be electric field for Q3 and Q4? Yes. So how will it be? Say suppose Q3 is giving some electric field E. So this enter the electric will this enter? Okay, yes, there will be different. So will this, my question is, will this Q3 electric field due to Q3 enters this closed loop? Can my electric field due to Q3 enter the closed loop? Yes, they can. They can enter. See, this was the same condition which we had in earlier case, right? Say in case of dipole, if you remember, in case of dipole, if you remember, which we studied in earlier class today, the number of electric field lines were moving out and same number of electric field lines were entering. What was the condition we used here, guys? What was the condition we used here? Say, yes, the electric field can enter, but how much amount of electric field enters this closed surface should also, the same amount of electric field should also leave. Okay. So net electric field inside this closed surface will still be zero, but the condition is, guys, yes, this electric field will enter the closed surface, but how much electric field will enter from outside, same amount of electric field should leave also. This is very important, guys. Please remember, whenever someone asks, can an electric field enter a closed surface? Yes, it can enter, but the condition is how much amount of electric field enters the closed surface, same amount of electric field also should go out. Okay, this we studied in the case of sphere, I mean dipole inside a sphere, right? For dipole, we had n number of electric field lines entering and n number of electric field lines exiting. Npedia, guys, please listen. So the Gauss law states that the net electric flux passing through the closed surface is given by, yes, many of you had given me this. It should go out, Nitanka. How much amount of electric field enters, the same amount of electric field should go out compulsorily. Okay. So the net flux passing through the closed surface is given as phi is equals to integral E dot dA, that is Q enclosed by epsilon naught. So the electric field due to Q3 and Q4 is not considered as they are not enclosed inside the closed surface. Again, I'm repeating. So the flux electric field due to Q3 will enter, but the same amount of electric field also will exit. ಎಷ್ಟು ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಎಂಟರ್ ಆಗುತ್ತೋ ಅಷ್ಟೇ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಆಚೆ ಕೂಡ ಹೋಗುತ್ತೆ. ಓಕೆ, ಹೋಗ್ಲೇಬೇಕು. ದಟ್ಸ್ ದ ನೆಸೆಸರಿ ಕಂಡೀಷನ್. Cool, guys. Then try to answer this. So what is the flux? Okay, hope you guys understood how to calculate or how to apply Gauss law. Yes. Okay, cool. So guys, again, so try to answer this question. What is the flux through the curved surface of the closed hemisphere? So the question is, what is the flux through the curved surface of the closed hemisphere of radius r? So this is a hemisphere, guys. So what they have given? They have given an hemisphere. of radius r, hemisphere of radius small r. Okay, I have an hemisphere of radius small r. Now, what is the electric flux? Karthik Gowda, check your answer. What is the electric flux passing through this? Oh my God. What is the electric flux passing through this hemisphere? Devika Rani, check your answer. Lakshmi, check your answer. Bhargav, check your answer. Ramakrishna Reddy, check your answer. Everyone, please check. Yes, Nitanka, correct. But why? Prajwal, correct. Why? Karthik Gowda, correct. Why? Why? Why is it so? Guys, try to answer. So why is my electric flux? Okay. So most of you answered the question, but I need why. Why is your answer that? Why did you answer only that? Okay. So I'm going to end this poll. So most of you had given option B as your answer, and option B is the correct answer. But why? So guys have given option B is the right answer, but why? Yes, correct, Bhargav. Madhavi, no. Yeah, I have given the right answer. That is option B. But why do you think option B would be the right answer? Yes, correct, Tejas. So, guys, yes. So let's check. Say when we have an hemisphere. So I'm trying to draw the side view. Okay, if I try to tilt this way, yes, if I try to tilt this way, what happens? So I'll try to draw an hemisphere. Okay, say yep. I got my hemisphere. Okay, if it was full sphere, option A will be yes. If it was full sphere, say if it was a complete sphere, proper sphere, then my flux would be E phi is equals to E dot A. E dot A, that is phi is equals to E into 4 pi r square, right? But here this is a hemisphere. Now what's happening? The number of electric field lines. Say if I have drawn my hemisphere in red color, I'll try to draw my electric field lines. Okay. So I'm representing my electric field lines in this way. Now what's happening, guys? Say here my electric field lines are passing through this, right? So what was the condition for closed surface? Electric field lines passing through closed surface. What is the condition for electric field lines passing through closed surface? Now, do I have a closed surface first? Do I have a closed surface? Do I have a closed surface here? Yes, correct, Bhargav. No, I don't have a closed surface. See, this is an open surface, right? So for a closed surface, I should have a closed sphere. For closed surface, I should have got a closed sphere. I mean, a solid sphere or a hollow sphere also. But here I have a open surface. Say the number of flux entering, the number of electric field lines entering is from the base, right? So large number of electric field lines enter through the base. What is the cross-sectional area of this base? What is the cross-sectional area of this base? Please reply. What is the cross-section area of this base? It is pi r square. Wow. Pi r square. So this is the circumference of the circle, right? Sorry, no, not circumference of the circle. It's the area of the circle. Yes, it's the area of the circle, right? So only through this area my electric field lines are passing. Only through this area my electric field lines are passing. On the other end, my angles or my area is continuously changing. My angles is continuously, sorry, my surface area is continuously changing. But see, in this case, my surface area is continuously changing. Whereas in this area, at the bottom, I have the same amount of area. So what's happening here? In this case, the area vector is different along the directions. So it should not be different for considering the Gauss law. For considering Gauss law, my area vector should not vary. So this was the condition, right? And one more thing, what's given by using Gauss law, there is no hemisphere does not have any charge enclosed. Again, so for applying Gauss law, phi is equals to q enclosed by epsilon naught. To use Gauss law also, my charge is not enclosed, or my charges or my electric field is not inside an enclosed surface. It's in an open surface, right? So my electric flux will be directly proportional to the number of electric field lines passing through an uniform area. So my uniform area was my flux through circular surface. So that is E pi r square. Okay. Yes, guys, got this? Any doubt? Any doubts, guys? Please let me know. Got this? Yes, no, reply Madi. Guys, did you understand this question? Yes, cool. So, yep, cool. So, why should we use Gauss law? So, what are the different applications of Gauss law? So, we'll come to the applications of Gauss law. In applications of Gauss law, we have the electric field. So, what is the first use of Gauss law? So, we can calculate the electric field due to continuous charge distribution. Say, in case of continuous charge distribution, if you remember, for checking the continuous electric field due to an infinitely charged current carrying conductor. If you remember, for the infinitely charged current carrying conductor, so we had used two small surface length dl, then we use the surface linear charge density lambda is equals to q by l. At a point r, this gives some electric field de in this direction. Try to resolve it, add it, and simplify it. We had done all this, right? So instead we can simply apply Gauss's law. Okay, so we can simply apply Gauss's law in this case to find the electric field in the case of a continuous charge distribution. Okay, how can I apply Gauss's law easily? So for that we have two conditions. Okay, this is the important condition. So we have to choose the Gaussian surface first. Before I apply my Gauss's law to any surface, I have to choose the Gaussian surface. So what is a Gaussian surface now? So we have to consider such a point. We have to consider, say, in case of a sphere or in case of a infinitely charged conductor, etc. In these conditions, to find the electric field, what should I do? I should consider a point. So I should consider my point such a way that the magnitude of electric field is uniform throughout the Gaussian surface. So I should consider my surface, the Gaussian surface should be such a way that my electric field, should be uniform throughout the surface. What does this mean? What does this mean, guys? What does this mean? This means my charge should be uniformly distributed throughout, right? When I have a sphere whose charge distribution is uniform throughout, then the electric field through this, the electric field due to this charge would be, or due to this charge sphere would be constant, right? Yes. Yeah. So considering the point in such a way that the electric field is uniform throughout the Gaussian surface, is my first condition. And the second condition goes like, I should choose the area. So the area for my dA, the area vector, should be such that, or my area of Gaussian surface should be such that it is symmetric over the Gaussian surface. The area which I choose should be in such a way that it should be symmetric Gaussian surface. Say if I consider this area, if I consider a point, say assume I have an electric charged, I have a continuously charged sphere, a uniformly charged sphere. Now if I have to find its flux, so I'll consider another bigger sphere. Yes, I'll consider another bigger sphere to find the flux through this. Okay, what happens if I consider irregular object? I mean, if what happens if I consider an irregular shape? Guys, what happens in this case? See, my electric field will still be constant, but I can't use my integration. If you remember, phi is equals to E dot dA, closed integral of E dot dA. If my area is not constant, I can't directly apply electric field. I can't directly simplify this for electric field. So if I want to find my electric field, I'll choose a area whose surface is symmetric. Okay, I'll choose, say if I want to find only the flux through this charge sphere, na not a ಇಲ್ಲಿ ನಾನು charge sphere ಇಂದ ಮಾತ್ರ electric field ಕಂಡಿಡಿಬೇಕಲ್ವಾ. So I'll take an electric flux, I'll choose a cover, or I'll choose the outer surface such a way that it is symmetric. See, anyway, my electric flux due to the charge condition, I mean, due to this charge sphere won't change. Irrespective of this surface area, my electric flux won't change, right? Will it change? What was the condition which my electric flux depended on? It depends only on the charge enclosed, and also, see, Gauss law states phi is equals to Q enclosed by epsilon naught. So my flux depends only on the charge enclosed and also only on the material medium. Please make a note of this, guys. My Gauss law states that the flux depends only on these two conditions. One is Q enclosed and my materials medium. Alba. Yes. So it does not depend on the surface area. So what I'll do to make my mathematical calculation simpler, I'll consider a regular surface area. I'll consider a symmetric area. Okay, that's the two conditions which we consider while calculating the electric field for continuous charge distributions. Okay, these are the two conditions. So why should we do that? I told you in earlier sections. Why should we do this? If I consider a regular symmetric surface area, I can consider my area vector parallel to that of electric field. Okay, now if I consider a regular symmetric surface area, then when I consider my area vector, ನನ್ನ area vector consider ಮಾಡಿದಾಗ, this area vector will be always parallel to electric field. That way I can eliminate cos theta. Guys, remember, you getting this? Why should we consider symmetric surface? Karthik Gowda, ಅರ್ಥ ಆಗ್ತಿದ್ಯಾ? Yes. So considering these two conditions, the magnitude of electric field will be constant throughout the surface and the electric field is parallel or antiparallel. So if I consider these two conditions, what are the outcomes of these two conditions? Why should I consider these two conditions? The first use is the magnitude of electric field will be constant throughout. So I can bring this magnetic electric field outside this integration. Then if I have a symmetric surface, then if we know that E dot dA is nothing but E dA cos theta. No, Nitanka, no. Only symmetric surface need not have continuous charge distribution. But my question is, what I considered here is, say if I have to find the electric field due to continuous charge distribution. ಹತ್ರ ಒಂದು continuous charge distribution ಇದೆ. Say if I have a solid, if I have a spherical substance or a uniformly charged conductor or a uniformly charged plane. So these three are the things which we saw, right? Or say any arbitrary shape which is uniformly charged. Okay, if I want to calculate for any of these conditions, if I want to calculate my electric field, what I'll do? So I'll consider its outer layer. This outer layer ಬರುತ್ತಲ್ಲಪ್ಪ. See, I'll have an equipotential surface for all of these, right? Say when there are electric field, because of these electric fields, because of the charges, produces an equipotential surface, right? So these equipotential surface I'll consider as what? My closed surface. Okay, we'll see that. See, if I go here, in this case of solid sphere, yes, yeah, it will. If I take symmetry, it will be easy for me. Okay, let's go step by step. Then the electric flux is given as phi is equals to integral E dot dA, that is q enclosed by epsilon naught. From the conditions, so what I can do, I get E dot dA is nothing but E dA cos theta. Say since because of symmetry, my electric field will be parallel to dA vector, then my theta will be 0 degrees. So cos theta will turn to 1 or minus 1. Cos theta will be having 1 or minus 1 as its value. So I can eliminate cos theta term from integration. So that makes my math life simpler. Again, guys, yes. Again, if I integrate and differentiate, say I have considered a small surface, right, dA. Now, if you observe this mathematically, how is it? Integral and differential of a function, right? This will be similar to integral of differential of a function. So what is integral of differential of a function? If I integrate and differentiate a function, I'll get back the same function, alva. So integral of this, yes, cancels. Integration differentiation cancels. I'll get total area A. So integral on differential of A will be nothing but A only. So this expression can be used to find electric field. So I can use this expression to find the electric field. Okay. You can use these expressions to find the electric field. Okay, this is the condition, guys. Okay, cool. So these are the necessary conditions which we get in our. We'll be discussing about the electric field in our next class. We'll be discussing about how to apply this formula. So we'll apply this formula of electric field to find the electric flux due to solid sphere. Then we'll try to find the electric flux due to uniformly charged conductor and also plane. Okay. E part artha agidya, guys. Have you understood till this equation? Please reply with yes or no. Everyone, yes. Any doubts so far? Any doubts so far? Any doubts so far, guys? So theta will never be 90 degree. Oh, theta will never be 90 degree in this case. If I consider symmetry, my theta will never be 90 degree. Okay, guys, any more doubts? So if you have understood this, try to answer this question. Yes, please try to answer this question. Assume that there is a charge Q1 inside a Gaussian surface. Okay, and a charge Q2 outside the Gaussian surface. So what's given? I have a Gaussian surface. Okay, I'll consider any arbitrary surface. So I'll consider any arbitrary surface. This is my Gaussian surface. Now, inside this Gaussian surface, I have a charge Q1. Outside this Gaussian surface, I have a charge Q2. So there are two statements given. then the net electric flux through the Gaussian surface is due to charge q1 only. The net electric field on the Gaussian surface is due to charge q1 only. So what is the right answer? Nitanka, theta may be 90 degree. It may be. It depends on the. If you are not considering a symmetrical outer surface, then yes, it will not be 90 degree. Then there might be, yeah, theta might be 90 degree. Nitanka. Yes, correct, Nitanka. So guys, yep, I have to share another poll, right? Yes, correct, Tejas. Correct, Karthik. YouTubers, please try to answer this question. Bhargav, check your answer. I gave you the condition. So when I was explaining this, I think I gave you the condition. Say have some arbitrary shape. Then I have charge q1 inside it and charge q2 outside it. So this is the condition. So if I have such a situation, what can I say about the electric flux and electric field? Note that guys, it's electric flux and electric field. So Ramakrishna Reddy wrong. Okay, now it's correct, Ramakrishna Reddy. Now it's correct. Madhavi wrong. Check your answer. Devika correct. Nikita Lakshmi correct. Prajwal correct. Nitanka correct. Karthik Gowda correct. Ashwani correct. Rakesh correct. So correct guys. So this is yep. So yep, I got to know, you guys got to know that. Answer is option B. Why? So if you see the net electric flux from Gauss's law, the net electric flux is given by Q enclosed by epsilon naught, right? From Gauss's law, the net electric flux is given by Q enclosed by epsilon naught. Then, yes, so the flux can be given as phi is equals to Q1 by epsilon naught in this case. But electric field will be because of this in all directions. Also, this the electric field due to Q2 also enters the Gaussian surface, right? The electric field due to Q2 also enters the Gaussian surface and also leaves the Gaussian surface. So the electric field is not only because of Q1, it's also because of Q2 too. So option B is the right answer. Yes guys, so hope everyone have understood all the concepts which was taught into you in the class. Yes. Cool guys, then we'll meet again on Thursday. Okay, we'll meet again on Thursday. Till then, if you have any doubts, please ask now, guys. Yes, it's Devika Rani, I didn't get your question. Did you ask something, Devika Rani? Okay, cool. Okay, guys, cool then. We'll meet again on Thursday. Okay. Okay, guys, bye.